So Dalton's law of partial pressure. This law is actually stated by a scientist called Robert Boyles. He actually tried to look at how the total pressure or the pressure of different gases. So, and as a result of that, he came up with a law where he stated that the total pressure of a given gas is, assuming now you have a container, and in the container you have a mixture of gases, and in the container you have a mixture of gases. Let's say this is your container and you have a mixture of gases. Let's say you have gas A and you have gas B, you have gas C, and then you have gas D. So now, how did you get the total pressure of these gases or of these individual gases? It is simple. He actually came up with the law to get the total pressure of the gases is just the summation of the partial pressure of the individual gases, because each of the gas is having its own partial pressure. So to get the total pressure of the gas is simple. It's just to say the total pressure of the gas, that is the P total, is equal to, we said that in this container we have four gases, A, B, C, and D. So for you to get the total pressure of these gases, is just you take the summation of the individual gases by saying the partial pressure of gas A plus the partial pressure of gas B plus the partial pressure of gas C plus the partial pressure of gas D. So if you now sum the partial pressure of these individual gases, then you are now going to get the total pressure of the gases. It's just the summation of the partial pressure of the individual gases. So also at the same time, when we are talking about pressure, we know that from our basic knowledge of chemistry, we know that pressure, which is P, is equal to force all over area. So we should all put this at the back of our mind, that whenever we set pressure, so pressure is equal to force all over area. So also at the same time, we have a formula for calculating pressure, which says Pv. We have a formula which says Pv is equal to nRT. The P stand for pressure, while V stand for volume, and N stand for the number of moles, while R stand for the universal gas constant, and the T stand for the temperature. And of course, when we said N stand for the number of moles. And of course, remember when we said mole is equal to mass all over molar mass. It's mass all over molar mass. And then when we set temperature, it can be measured in Kelvin, it can be measured in degrees centigrade. But usually in this case, whenever we have a pressure, whenever we have temperature in terms of degrees centigrade, we usually convert it to Kelvin. So also at the same time, we have what we call a mole fraction. We have a mole fraction. So if you want to get the mole fraction, we have a formula, mole fraction. And this formula for mole fraction is represented to be Xi. So Xi stands for mole fraction. And how did we get this mole fraction? This mole fraction can be in the form of Ni all over N total. What is the meaning of Ni? Ni means the number of moles of I divided by the total number of moles. So you can get mole fraction in terms of mole. So mole fraction can be number of moles of I divided by the total number of moles. And it can also be, at the same time, it can also be volume of I divided by the total volume. So it can be Vi. So when you said Vi, it means the volume of I divided by the total volume. So also at the same time, it can be Pi. It can be Pi. It can be Pi all over P total. So when you said Pi, it means the partial pressure of I, or the pressure of I divided by the total pressure. So it can be in form of this. So let's say now, for example, we have let's say we have two gases. Let's say we have two gases. We have two gases. Let's say you have a container, and this is the container, and in the container you have, let's say, gas A and gas B, and you now want to calculate the mole fraction of this gas. And how do you do that calculation? Is simple. How do you do it? It's simple. You just say, maybe you are already having the number of moles of A and B. So how do you do the calculation? You just say is equal to, let's say, the number of moles. Maybe you want to get the mole fraction of A. So to get the mole fraction of A, you are now going to say Na. When I said Na, it means the number of mole of A divided by the N total. When I said N total, it means the number of mole of A plus the number of moles of B. That is the same thing as you have Na, it's equal to number of moles of A plus the number of moles of B. So you can have a situation where you are not actually given direct the moles of the molecules. So if you doesn't have that, what do you do? Maybe you have the mass, and of course you have the element with its molar mass. So you have to calculate the mole. So that is this. And also at the same time, you can also have, and at the same time, the mole fractions of each and every individual gases is always equals to unity. Let's say you have a mole fraction of A plus the mole fraction of B is always equals to unity. When we say it's equal to unity, it means it's equal to 1. It's equal to 1. So let's actually give an example. Assuming now, assuming now you have a container. That contains two gases. Let's say in the container you have nitrogen gas and you have oxygen gas. And the mass of oxygen gas is, the mass of nitrogen gas, let's say, is 7 gram, and then the mass of oxygen gas, let's say, is 16 gram. So you have the mole of nitrogen equals to 7 gram, and the mole of oxygen, the mass of nitrogen is 7 gram, and the mass of oxygen is 16 gram. So now let's say you want to calculate, or let's say what is the mole fraction? What is the mole fraction of oxygen? So let's say this is the question. You have a container, and in the container you have two gases. You have nitrogen gas and you have oxygen gas, and you're asked to calculate the mole fraction of oxygen. So how are you going to do it? Of course, in many cases, you will be given the mass of nitrogen. Let's say the molar mass of nitrogen is equal to 14, and then the molar mass of oxygen is equal to, let's say, usually we don't use these two. Let's say because we are talking about oxygen. So let's say the molar mass of oxygen, is 16. So now how are we going to calculate the mole fraction of oxygen? Then it's simple. We have to first calculate the molar mass of nitrogen and then the molar mass of oxygen. And remember that nitrogen is always diatomic, that is, it's usually come as 2. So the mass of nitrogen is 14. So we are now going to say 2 times 14, which is equal to 28 gram per mole. And that is the molar mass of nitrogen. And then for the oxygen, the molar mass of oxygen is of course 16, and it's usually also come as 2. So we are now going to have 2 times 16. So 2 times 16 is 32. We have 32 gram per mole. That is the molar mass of oxygen. So now what are we going to do next? We are actually going to calculate the mole of individual gases. So therefore, now the mole, which is N, the mole of nitrogen is equal to mass of nitrogen is equal to mass of nitrogen divided by the molar mass of nitrogen. So therefore, the mass of nitrogen from the questions is 7 divided by 28. Then is equal to, then we now calculate this. We now calculate the mole. So therefore, we have 0.25 mole of nitrogen. And then the next thing is the number of moles of oxygen. So therefore, we have the number of moles of oxygen is now equals to the formula, which is mass of oxygen divided by the molar mass. Therefore, we have 16. The mass of oxygen is 16, and then the molar mass by 32. So we now have equals to 0.5 mole. So we have 0.5 mole as the number of moles of oxygen. So you see now we have the number of moles of oxygen and the number of moles of nitrogen. So the next thing is to get the mole fraction of oxygen. And how do you do it? So now we are now going to say the mole fraction of oxygen is now equals to the number of moles of oxygen divided by the number of moles of oxygen plus the number of moles of nitrogen, which is now equals to the number of moles of oxygen is equal to 0.5 divided by 0.5 plus 0.25, then it's now equals to therefore finally we have 0, we are going to have 0.67. So it doesn't have units. So therefore now the mole fraction of oxygen is 0.67. So we now have 0.67. So now you have the mole fraction of oxygen. So let's say now you are also wanted to calculate the mole fraction of nitrogen. I think it's simple because I told you that the mole fractions of any gases or the mole fraction of any number of gases is always equals to 1. So therefore, we are now going to set the mole fraction of oxygen plus the mole fraction of nitrogen is equal to 1. And of course, the mole fraction of oxygen is already obtained as 0.67 then plus n. Sorry, plus xn. Plus xn. This one's supposed to be xn, that is the mole fraction of nitrogen, then is equal to 1. So it means that now the mole fraction of nitrogen is equal to 1 minus 0.67, which is equal to 0.33. So this one is our final answer. So this is how to calculate the mole fraction of a gas. So a mixture of hydrogen gas and oxygen gas exerts a total pressure of 1.5 atm on a wall of its container. So if the partial pressure of hydrogen is 1 atm, find the mole fraction of oxygen in the mixture. So you see here we have two gases, and in these two gases we have a mixture of oxygen and hydrogen. And of course, the total pressure is 1.5 atm on the walls of the container. So if the partial pressure of hydrogen is 1 atm, then how are we going to get the mole fraction of oxygen in the mixture? So I think, ladies and gentlemen, we can clearly see that this question is also simple. And how did you get the answer? We are now going to say solution. solution. So we have P total. We have our P total. Our P total is equal to 1.5 atm. And then we have the partial pressure of hydrogen to be equals to 1 atm. 1 atm. So now how are we going to get the mole fraction of oxygen? I think it's simple. It's simple. We are now going to see from the formula which says P total according to Dalton's law of partial pressure. So the total pressure of these gases will be the partial pressure of hydrogen plus the partial pressure of oxygen. So we have this. And of course, our P total is equal to 1.5 atm. Then it's now equals to the partial pressure of hydrogen. So the partial pressure of hydrogen is 1 atm, then plus the partial pressure of oxygen. So how are we now going to do? This one is also simple. So we are now going to set 1.5 atm minus 1 atm minus 1 atm minus 1 atm is equal to the partial pressure of oxygen. So therefore, 1.5 minus 1, we have 0.5 atm, then is equal to the partial pressure of oxygen. So it means that the partial pressure of oxygen is 0.5 atm. So how are we going to calculate the mole fraction of oxygen? It's simple. So to calculate the mole fraction of oxygen, we are now going to use the formula which says the partial pressure of oxygen. The partial pressure of oxygen is equal to the partial pressure of total. So the partial pressure of oxygen is 0.5. Then we are now going to say divide by the P total, which is 1.5. So 0.5 divided by 1.5. Ladies and gentlemen, what do we have? We now have 0.33 as our final answer. So we have another question here. Suppose there are three gases, argon, nitrogen, and oxygen, which are mixed in a container of 500 ml. In addition, the pressure of nitrogen is 228 torr, hydrogen is 752 torr, and argon is 254 torr. Now calculate the total pressure in the container. So you see, I think you can clearly see that all these questions are very simple, or these questions is simple. You are just given a partial pressure of the individual gases, which is nitrogen, oxygen, and argon. So to get the P total, I think you can clearly see it's simple. How are we going to get the P total here? To get the P total, we are now going to say P total is equal to the partial pressure of nitrogen plus the partial pressure of argon plus the partial pressure of hydrogen. So to get your final answer, you just sum them together by saying 255 plus 228 plus 252. So you just sum them together. Whatever you get is your final answer. So ladies and gentlemen, we are going to rejoin again because it is elapsing now. So we are going to rejoin again. Okay? We are going to rejoin the meeting again.